All right, hello. So this is a recorded lecture. This is going to be looking at processes and threads and the message passing interface, which is a way of coordinating processes across very large computers. So up to now, we've been using OpenMP. The way that we've been exposing parallelism is at the instruction level, looking at vectorization, instruction level parallelism, and then at the level of threads. And turns out threads and processes are very similar. So on Linux, which most HPC systems are running Linux, they're actually created by the same system call. It's called clone. And they're scheduled in the same way by the operating system. Both of them have their own stacks, their own control. They're executed by cores in much the same way. They have access to the same memory upon creation via, say, fork or clone. But there are some important distinctions. So threads set this flag called clone VM. This means that they share the same virtual to physical address mapping. So for example, threads can access the same data as all the other threads. They can access it at the same address. So the virtual address, which is what you see within your program, is the same. And the only way that data stays private is because other threads don't happen to know the address or access that address. But there's no safety provided by the operating system. Processes are different in this regard. They will, in general, have separate addresses, and you can't access the memory. They have a different virtual to physical mapping. Threads also set a few other flags like clone files, which means that they share file descriptors. So if a file descriptor is open by one thread, any other thread can use that file descriptor. File descriptors are just numbers, but they go to accessing files. Threads also set some other flags like clone thread and clone sig handle. So these aren't really important for our purpose right now, but they're observable differences between threads and processes. So there are some common myths about processes. Some people would say processes can't share memory, and that's just plain not true. So you can use these functions like shmem open. You can also use MPI interfaces like MPI win allocate shared. This provides a portable way for different processes to get access to shared pieces of memory. It is true that that memory could be at different addresses, but if you have something that you want to share, you can share it. The substantive difference is that with threads, everything is shared by default. And so usually you have to do some work to make sure that things are separate. That also can make things a bit harder to debug. With processes, everything is private by default, and you only share what you put effort into sharing. Some people would say that processes are heavy. So heavy isn't a precisely defined term, but let's think about some of the differences, or similarities. So threads and processes use the same data structures, the same kernel scheduling. There's basically no difference in their context switching overhead. They do have the different virtual to physical mapping, but this is usually a pretty minor factor. Data from the parent, that is when you create a thread or create a process, it's inherited copy on write at very low overhead. So for example, startup costs for a process might cost about 100 microseconds. And a lot of that is in duplicating the page tables, but not any of the actual memory. So this copy on write is efficient. It turns out to be very important for the way that modern operating systems work. But the kernel does that sort of thing very well. Also, caches are physically tagged, which means that The virtual address is translated to a physical address before it gets looked up in the cache, even in the level 1 cache. And that means that separate processes can share the same level 1 cache. And so basically, most of the programming techniques that you would use, certainly the algorithms that you might express with threads, are also possible to be expressed using processes. And probably the overheads for doing that will be very low. They'll be very similar between processes and threads. So the big difference is shared by default versus private by default. So the message passing interface is a kind of standard way in high performance computing for programming with multiple processes. And those processes need not live on the same host. They don't need to be on the same node. They can in fact be on different computers in different parts of the world. MPI is just a library. So you use a normal C, C++, or Fortran compiler. This is really different from OpenMP. So OpenMP is a language feature. It's kind of an extension, this set of pragmas. The compiler has to be aware of OpenMP, and you're kind of asking the compiler to do certain transformations of your code when you add the OpenMP annotations. With MPI, there's none of that. And there are two popular active open source libraries. They're actually the basis for essentially all MPI implementations that are used these days. And because they're open source, it means you can go into the source, you can modify things, you can relatively quickly experiment. Say if you're doing research at the systems level, you can go dig down in there and investigate. So these implementations are called MPICH, MPICH, and OpenMPI. And they're both available through the distribution manager on most Linux systems. Sometimes particular facilities will choose one or the other, or a vendor implementation, which modifies these open source implementations. There's also one that's popular on some high performance computing systems called MVAPICH, which is an open source implementation. It's based on MPICH, and it's intended for InfiniBand and some related high performance networks. There are bindings to MPI from various languages. So for example, MPI for Pi is quite popular. It's a Python library, allows you to have low-level access and also somewhat higher-level access to essentially everything in MPI. So MPI is highly scalable. So for example, it's been run on over 100,000 nodes with several million processes, I think over 10 million processes. This is something that's really not achievable with OpenMP. And a big part of this is that coherence is very expensive. And so there are big shared memory systems, much bigger than you might think of 2, 4, 8 sockets. For example, there are some SGI, it's their UV line, that has like up to 1,000 sockets. It has at least several hundred sockets, up to say 4,000 cores that they claim to support. And so you'll see systems like that with several tens of terabytes of memory, pretty large systems, but they're very expensive. If you look at the cost per core or the cost per socket, the cost per DRAM channel, it's going to be much higher than to take simpler nodes, say nodes with 1 or 2 sockets. And you're going to pay a significant cost in terms of latency, because to implement this view of shared memory, this coherent shared memory system, it requires a lot of work. And so your latency that, say on a normal system might be 100 nanoseconds, that latency goes up quite a bit when you start building larger systems. And you pay for that latency every time you access memory, versus when we use MPI, there will be a latency for communication, but we only pay it when we have to actually communicate. So standard usage of MPI, the processes are all separate on startup. So this is a little bit like if you take OpenMP and you stick an OMP parallel right as the very first thing in main, and everything you do inside is parallel, and you never use OMP single. Turns out with OpenMP, not many people program that way. Maybe we should more, but the standard usage of MPI is that a resource manager or the job launcher creates processes that may be on separate machines and provides the information so that they can talk with each other. And then your application takes it from there. And we'll see an example here in a moment. So the timeline for MPI, the first version of the standard was completed in 1994. That included point-to-point messaging, collectives, something called data types. But these are the basic primitive operations that are used by most any MPI program. A few years later, the standard grew by quite a bit. So MPI 2 came in 1997. It added parallel I/O. This was really important for applications that had to read and write data from parallel file systems. It allows abstracting that level of processing, that interfacing with the parallel file system, which used to be kind of more nuanced and manual than under MPI 2. It also added some functions like MPI spawn that allows you to create and destroy processes from within your application. The trouble is that those kinds of primitives are often not supported on HPC systems, and so you have to be a little bit careful around that. And MPI 2 also added one-sided operations, so you can put or get memory. It's a quite low-level primitive, but you can put or get memory from other processes without their knowledge, without them doing anything on their side. We'll have an example of what that looks like later. Then there was quite a bit of time, 15 years, until MPI 3 came along. And there were a couple modifications. There's a MPI 2.1, 2.2 that I skipped here. MPI 3 came along in 2012, and it added some really cool features like non-blocking collectives. So this is a way of doing operations like a reduction, where you post the data for it, but you don't wait, you don't block until it completes. Instead, you post the data for it, and then sometime later, maybe after you do some more local computation, you can ask for the result of that reduction. It also added neighborhood collectives, which are a pretty cool feature. Unfortunately, most of the vendor implementations are not very optimized, and so it works out to the same kind of communication as the point-to-point messaging. MPI 3 also added improved one-sided. So the choices that were made in MPI 2 turned out not to be ideal for a lot of applications that wanted to use one-sided, and MPI 3 rethought that and provided it in a very flexible and powerful manner. So let's look at an example here of using MPI. So up top, we include MPI.h. This is the header that allows us to call MPI functions. Everything in MPI is namespaced, and so every function related to MPI, every named constant, things like that, are going to be MPI underscore something. So we call MPI init, and we pass in the arguments. This is because it's possible for job launchers to specify parameters for the MPI application through arguments in this way. And so MPI will pull out the arguments that are important to it. It turns out usually this doesn't matter. So most of the time you could get away with just passing null through there. So then at this point, as soon as you enter main, these processes are separate. They may be running on separate machines in different continents. They have information about how to communicate with each other. They can communicate over various protocols. But in order for us to make a parallel application that does something useful, we want each rank to do something different. And so usually that's computed from the rank. So there are these functions, MPI com rank, MPI com size. So size says how many processes there are, and the rank says what is my index, am I 0, 1, 2, and so on. These have a parameter that comes in, it's MPI com world. So if you recall with OpenMP, we had something similar. So we had an OMP get thread num, which you can think of as being basically the same as MPI com rank. An important difference here is with MPI, we have this argument where we pass in a communicator. Communicators are really powerful. They are as an abstraction, as a way of writing libraries or composing code. Communicators can be split, so they can be of different sizes, and it really allows libraries to encapsulate what they do without interfering with possibly other things that are going on in the parallel application. So in this case, we're going to do a reduce, and this is all reduce, which means that all processes get the result. And so we pass as an input parameter, we pass in the rank, and these are, everything here is treated as kind of arrays, or there's a count number of items. So there's one item in rank. We're just thinking of this integer rank up here as being an array of length 1, we pass in its address. And the output from the all reduce is going to be sum, which is also an array of length 1, i.e. one value. And in MPI, we have to specify what the types are, because in C, there isn't a way of automatically communicating that kind of information. So we pass MPI int. This is a built-in data type. Turns out there's data types that we can create, so we can have much richer abstractions. But here we use the built-in data type, MPI int, and we want to sum the result. And this is the built-in MPI sum. Turns out that the operations are also extensible. So we can write custom reductions where the combiner operation is code that we get to write. But ultimately across this, we call with those parameters and on MPI com world. And this is the blocking all reduce. So it doesn't return until it actually has the result. So then we're going to say, let's print this out, and we'll call MPI finalize. So somehow we have to compile this. It's a normal compiler, but most of the time we'll use the compiler wrapper MPI-CC. MPI-CC is really no magic. It just calls the compiler with some flags. It saves us having to write out those flags. If we switch to a different MPI implementation, we'll have, say, a different path to our MPI-CC, and it will set up the compiler flags appropriately. You don't have to use the compiler wrappers. You can just say, call this show. You can pass these parameters in as, say, LD flags, LD libs. That would also work just fine. So we can compile our demo program up here. This is compiling this program. And we go ahead and run it. So to run MPI with multiple processes, we use MPI exec. And this says -n2, that means use 2 processes. And then we run the application. We could pass other command line arguments to the application. This is running locally on my machine. So in some sense, this is similar to if we had used OpenMP. We could create an OpenMP program that has a structure kind of like this, where the very first thing in main creates an OMP parallel region, and then we get our rank and size, and then we do operations. However, OpenMP reductions, things like this, are not nearly as expressive. And what happens much more frequently if people do OMP parallel, they also do OMP single, and then they're handing out tasks. And that works, but it's it's less extreme sort of parallelism. In MPI, everything is parallel, and if you ever want synchronization, you have to use the interface, call MPI functions to communicate data. So we use MPI exec here. It's very much like, OpenMP. If I had said OMP num threads equals 2, and then I could try again, OMP num threads equals, say, 6, and run that again. Basically the same thing here. With some MPI implementations, you'll have to add a flag like oversubscribe. With others, you won't. So I have 4 hardware cores, hardware threads on this machine. And so if I want to run 6 jobs with a recent version of OpenMPI, then I'm going to need -- oversubscribe. The reason for this is that oversubscription is usually expensive. Expensive like 100x. It can slow your code down by, say, 100x to have oversubscription. And the reason for this is MPI implementations are optimized for latency. So they want to keep the number of, say, the number of cycles minimum when you do an operation like MPI all reduce or send and receive, things of that sort. And so because they're trying to keep that latency really low, they often do a spin wait, a kind of busy wait, where the process is constantly checking a piece of memory to see if some update has occurred, an update that's expected to come from another process or from the network. It's possible for an implementation to call into the kernel and say, block until this kernel event happens, but it's quite a bit more expensive. And so if you are not oversubscribed, then your application, if it's sensitive to latency, will tend to run faster the way that MPI implementations work. But oversubscription is an important concern to keep in mind. So you can use OpenMP within the ranks of MPI. There's MPI init thread, which is an interface that allows you to specify kind of how are you going to use threads with OpenMP. How are you going to use threads, which could be OpenMP or a different system, with MPI. But the important thing is, between MPI ranks, everything is private by default. If you want to share something, you have to do it explicitly. So there's a nugget of advice here from Bill Gropp. So Bill Gropp was the primary author of MPitch. He had a system called Chameleon before that. And when the MPI forum was meeting to come up with the specification, after each meeting, Bill would go implement things, and he would come back with, here's the results of this implementation. Here's what works. Here's what didn't work. Things of that sort. So he's been a driving force with MPI since the very beginning. He was also one of the creators of PETSI, which is a parallel solvers library that I have been developing for quite a while. Started back in the 90s by Barry Smith and Bill Gropp at Argonne National Lab. And so he says, you want to think about how to decompose your data structures, how to think about them globally. If you were building a house, you'd start with a set of blueprints, gives you a picture of the whole house. You wouldn't start with a bunch of tiles and say, well, I'll put down a tile on the ground and then I'll go find a tile to go next to it. But all too many people try to build their parallel programs by creating the smallest possible tiles and then trying to have the structure of their code emerge from the chaos of all these little pieces. You have to have an organizing principle if you're going to survive making your code parallel. This is part of a kind of interesting research, computing, and engineering podcast. It was actually several years ago. But it's totally worthwhile if you're interested in the kind of history of MPI. You can go listen to that. So much more than OpenMP, MPI requires us to think ahead of time about how to decompose things. With OpenMP, often we can get started. We might not get very far, but often we can get started by just diving into our code, finding things that are expensive, deciding when something is big enough to justify using, say, OMP4, and work very incrementally in that way. With MPI, usually we really got to put some legwork in at the beginning about how to decompose things, but the rewards usually pay off. So I mentioned these things called communicators before. So when we create our program, we have this MPI com world. It's basically a named constant that contains all of the ranks that we created with MPI exec. Those ranks could be on different nodes. They're set up so they know how to communicate among each other. We can send messages, we can do reductions and other collective operations. There's another named constant that's similar to that called MPI com self. So a lot of libraries, anytime you call something on the library, you pass in a communicator. And that tells the library, what scope am I working on? Am I doing something that is local to this process? Am I doing something that contains, say, this collection of 2 or 4 processes? Does it contain 1 million processes? We express that through communicators. And communicators can also have some attributes, some other components. So we can create new communicators from existing communicators. The simplest mode of doing that is MPI com dupe. It creates a new communicator that shares the same size, shares all of the same ranks, but it's like a separate namespace. And so often a library, when it's first called, it will get a communicator in, and it will internally create a communicator using MPI com dupe for everything that it does. So then when it sends messages, it chooses tag values and things like that. Those won't collide with other messages that other libraries might be sending around in the program. It's very important abstraction, really allows us to write reliable libraries that don't have kind of weird dependencies or assumptions. We can also create communicators that are smaller. So for example, we can use MPI com split. This allows us to split an existing communicator into smaller pieces. And once we split it, all operations on that smaller piece are entirely self-contained. They don't involve any of the other ranks. They only involve those on each of the split communicators. And there's some more advanced functions like MPI com create and MPI com spawn, which is capable of creating new processes. We can attach attributes to these communicators. That turns out to be pretty useful for library composition. So what can we do with the communicator? Collectives are one version, one kind of way of expressing our algorithms. When we can map our algorithms to collectives, we benefit quite a lot because collectives tend to be implemented very well, and they are kind of simple, powerful ways of expressing components of a parallel algorithm. Usually we don't want to be writing things like collective operations by hand because that will tend to be quite a bit slower. Also, it's a bunch of code that we have to write. So the one that we've seen used already is called MPI all reduce. So this allows us to have some send buffer that's provided by every rank. And there's a receive buffer, and at the end of the MPI all reduce, everyone is going to have the same values in their receive buffer. There's also an MPI reduce. And with MPI reduce, it looks basically the same, except there's one new argument called the root. And when calling MPI reduce, everybody has to agree on who the root is. Often the root will be, say, rank 0. And so we call MPI reduce. Everybody passes in data. So it's very much like all reduce, except only only the root gets the result. So the receive buffer is only valid at the root. And so you might think, oh, that's probably cheaper than all reduce. And it turns out that's not always the case. So there are some machines in which all reduce is very well optimized and actually cheaper than reduce. And it's a little bit unintuitive, but basically the network is set up in a way that all reduce is extremely efficient. The fastest way to do any sort of reduce is to do an all reduce. And so even just running the all reduce and kind of discarding the data that isn't used at all but the root node is in fact more expensive than just calling all reduce. There's also a scan. So we've seen scans. We saw that OpenMP has some support for scans. So the idea is send buff from every rank. And say if we use an operation like MPI sum, which just adds all those values up, then on rank 0, it's just going to have its send buffer. And so that's just going to be written into the receive buffer. But on rank 1, it's going to have the sum of what was sent from rank 0 and what it had in the buffer on rank 1, and so on all the way up to your last rank. So these are the kind of popular scalable collectives. There's some other variants to these, but all of these have a total data size on any given rank that's proportional to what you're putting into it. Gathers and scatters are a little bit different. So gathers and scatters allow some rank, say the root rank, to gather data from all of the other ranks. And so you can imagine, well, one way to do that would be to just send from all ranks over to the root rank. Turns out that's not an optimal way to do things. The root rank in that case would have to receive, say, thousands or even millions of messages. There's some overhead to doing all of that. And so it's better for implementations generally to aggregate along the way. But only one rank ends up with this result. And if you send more than a very little bit of data, like one integer, to if you so the send buffers on each rank have to be the same size, and that's this. Oops, sorry, that's the send count here. And if you send more than a little bit of data, then whatever is going to end up on the root, if you have a lot of processes, that's going to be pretty big. So it's not scalable in a sense, but if that's what your application needs, then that's what it needs. Similarly with scatter, this is where one root has some data that needs to go to all of the other ranks, and it's a separate piece of data for each of the other ranks. And so MPI scatter will do that efficiently. So the implementations of some of these operations are, they're often tuned by vendors, and they can be very fast. So this is an example on BlueGene, which had a phenomenal network. This model of machine is actually retired now. But what we see here are different color lines for different number of ranks. So from 4,000 up to 130,000. And so all these colored lines here, these are the time it takes to execute an all reduce on this number of processes. And we see that it's nearly constant time. We also see that for small messages, say up to size of, say, 40 or 50 words, which is working out to a few hundred bytes. So up to that level, it basically costs the same to send one as to send several. And after that, we enter this regime where the cost increases, kind of dependent on throughput. It's more dependent on bandwidth. And there are some messages you get bigger and you see like an extra sort of jump. And that's pretty typical to see these sort of anomalies when you draw a curve like this. All the yellow lines down here, this is just the cost to send a single message between two ranks. So AllReduce is only costing, say, 3 or 4 times as much as sending a single message. So this is actually kind of amazing. If you were to try to implement this yourself, you would expect that the cost of AllReduce scales something like a log of this total number of processes. But that's not what we see. We see it being almost constant time. So in addition to collectives, MPI has point-to-point messaging. So this allows us to send and receive between ranks. And so one version of this is a blocking send. So one rank says, okay, I want to send data over to this other rank. This one calls MPI receive, says, who am I expecting to receive data from and where should it go? Whereas this one says, who am I sending it to and where's the memory that it's coming from? It is also possible to do an immediate or non-blocking send. And so the way this works, the sender says what data it has, where it's supposed to go, but the function returns immediately. And somehow in the background, this might be offloaded to a network, might be offloaded to some other thread or process on that node that's going to manage transfer of that data. But MPI ISend returns immediately. And then when you want to know that it's actually complete, say to reuse this buffer in your memory, you have to MPI wait on it. And then similarly over here, we can call an iReceive. This will return immediately. It says, I'm expecting a message from rank whatever, and I want it to go here into this piece of memory. And so it also returns immediately. And when you want to actually use what's in that memory, you call MPI wait. So we have blocking version, we have non-blocking version. When you call the non-blocking or the immediate versions, it returns an MPI request, which is what you have to wait on. And there's functions that can wait on several of those at once. If we use the blocking interfaces, we have to be really careful about deadlock. So say we want to send messages in both directions. We want to send a message this way, but we also want to send a message back. That's going to be problematic with the MPI send, because my send isn't guaranteed to complete until the receive over here has been posted. And if I have a send sitting down here, it may not complete until the receive has been posted. And so we would have to somehow choose for every process who sends first and who receives first. And it's very complicated to do that if you have several neighbors. If we just both call send first, then we could both block waiting for somebody to call receive, which would never happen. We call that deadlock. In practice, I never use blocking send or receive. I only use things like ISend, iReceive. There's also some variants like synchronous send, which guarantees that it doesn't complete until a receive has been posted. There's one called buffered send. There's non-blocking variants of those, like MPI ISend. I never use those either. In fact, I think most of them could be removed from the standard. There's one really cool exception for MPI ISend, but we'll talk about that later. So point-to-point messaging is kind of like the assembly language of parallel computing. It can be good for building libraries. It's a total headache to use directly for most purposes. So basically every MPI application or large library is going to have some code that they've written. Probably it uses these point-to-point primitives at some level, but they're exposing a higher level abstraction, and then the rest of that library or application uses that higher level abstraction. And this was an explicit intent of the MPI forum. When they were writing the standard, they wanted these kinds of libraries to be make it possible to write these sort of interfaces that were in a way that's reliable and maintainable. So when we can, we like to use collectives. We like to create our own functions that have collective semantics. They might be implemented in terms of point-to-point messaging, but rarely would we use point-to-point messaging directly in an application. So a lot of parallel computation involves communicating with some set of neighbors. And that set of neighbors is usually a small fraction of the total number of ranks in a parallel system. Often we have to do the same communication pattern many times in sequence. So for example, we might have an iterative solver. We might have time steps. We have to communicate to the same batch of neighbors on each one of those steps. We might not be changing who the neighbors are, or if we do, we only do that relatively rarely, and then we do the same pattern quite a lot. And so MPI has a few interfaces to do that sort of thing. So one would be what we've already seen. So you can use point-to-point messaging, I send, I receive, await all. So say this process might, I send all of the outgoing arrows. So it has 4 outgoing arrows. It posts all 4 of those. And then it might I receive for the 4 incoming messages. And it has to calculate what it thinks the rank of these neighbors is. And so it posts those I receives. And then it might call await all on those 8 MPI requests. There were 4 outgoing requests, 4 incoming requests. Call wait all on that. And when we complete, then we can go on with the rest of our application. There's also what's called persistent point-to-point, where we call MPI send init. This is something that we call once. It doesn't actually do any communication. It just identifies buffers, kind of gets this description of what send or receive I want to do. And then there's an MPI start all. So I can have a batch of these, say, sends and receives that I initialize. And then on each iteration, I just call an MPI start all and then an MPI wait all. So that's it's a common pattern. It's been around since the early versions of the standard. It's useful. In most cases, it'll have about the same performance as the point-to-point, but there are some systems where the send init can use direct memory access with a bit less rendezvous. So basically, processes agreeing on where in physical memory transfers need to go. And so for some sizes and on some hardware, MPI send init will be faster than just calling I send and I receive. Even if it is not faster, it should never be slower. There's a different strategy called neighborhood collectives. And this is something that we'll do a few experiments with those. It's a relatively new interface. It was added in MPI 3. We have to create a special communicator that kind of embeds this neighbor information. But then it allows us to have an interface like collectives, where we post all of the information that we need to send or receive into one function call that communicates with all of the neighbors in that process topology, which is part of the new communicator. It's also possible to implement these sort of operations using one-sided communication. So one-sided communication are things like puts and gets. They can be very efficient, but you have to manage some safety yourself. And so there's kind of different levels of synchronization, and one-sided can be sort of complicated to get right. Usually what you have to do to get it right is essentially the same as these other interfaces. And so I would say for most purposes, there's no particular advantage of using one-sided, but there are some times when you have application information that expresses itself sort of cleanly to one-sided, and so sometimes that can be a good choice. So thanks. I'll see you all on Friday, and maybe you'll get a chance to play around with, well, certainly we will do some experiments in the lab on Friday, and then we'll go more into kind of how to express algorithms using MPI during the lecture. Thanks a lot.